Medhavy AI, Intelligent Learning Systems. In this deep dive, we unpack the infinite square well, Chapter 5 of Quantum Mechanics, Volume 1. Let's get into it.
Methodical. In 1993, physicists at IBM's Almaden Research Center used a scanning tunneling microscope to arrange 48 individual iron atoms on a copper surface. They were looking at the electron density trapped inside that ring. The images reveal a series of concentric rings. This standing wave pattern of probability density proves that matter behaves like a wave when it is confined to the atomic scale. Think of a guitar string fixed at both ends. When plucked, it vibrates at a fundamental frequency and its harmonics because the wave must vanish at both fixed endpoints. A half wavelength fits, and a full wavelength fits, but 1 and a third wavelengths cannot exist because they contradict the boundaries. We model this with the infinite square well. Inside the box, potential energy is 0. Outside, it shoots to infinity, creating perfectly rigid walls. Particles cannot exist there, forcing the wave function to be exactly 0 at both boundaries. These conditions dictate to physics. Quantization emerges as a mathematical necessity of this confinement. The boundaries themselves determine which modes are allowed to survive. Inside the well, the Schrödinger equation is a spatial oscillator. Its general solution is psi of x equals a sine kx plus b cosine kx. At this stage, any energy is possible. The wave vector k can be any positive number. We apply the first boundary at x equals 0. Since the wave function must be 0 here, the cosine term, which is 1 at the origin, must be eliminated. Setting the constant b to 0 leaves us with a pure sine wave, a sine kx. Now we test the right boundary at x equals L. For the wave function to vanish here as well, the term a sine kl must equal 0. A sine wave only crosses 0 at integer multiples of pi. This forces kl to be exactly n pi, where n is an integer. The continuous range of possible wave vectors collapses into a discrete ladder. In 1913, Niels Bohr postulated that electron orbits were quantized to explain experimental data. He assumed the rungs existed because they had to. 13 years later, the Schrödinger equation showed that quantization is the only way a sine wave can satisfy two physical boundaries simultaneously. It was no longer a guess, it was a derivation. This is the resulting energy formula. It shows that the allowed energy levels are locked to the physical properties of the system. The energy values are determined entirely by the mass of the particle and the width of the container. Narrowing the box or reducing the mass pushes the energy levels higher. If we place an electron in a 2 nanometer well, the ground state energy is approximately 0.094 electron volts. Because the energy scales with n squared, the ladder rungs spread out as they climb. The second level is exactly 4 times the energy of the first, and the third is 9 times higher. A trapped electron will only interact with energy that matches these specific rungs. It ignores any input that would land it in the gaps between them. In 1926, Erwin Schrödinger submitted 4 foundational papers establishing wave mechanics. He showed that quantization could be derived directly from the boundary conditions of a wave equation. In our energy formula, the index n cannot be 0. If the energy were 0, the wave function would be a flat line, meaning there is no particle in the box. Werner Heisenberg's uncertainty principle explains why. A stationary particle would have 0 momentum spread, but because the particle is confined to the box, its position is already restricted. The ground state uncertainty product is roughly 14% above the absolute mathematical floor. It represents the most localized state the laws of physics allow. This minimum non-zero energy, or zero-point energy, is the unavoidable kinetic cost of confinement. These are the first 3 allowed wave functions. When we square them, we see the probability density, the standing wave patterns that dictate where the particle is likely to be. Each step up the ladder adds exactly 1 more node, a point where the probability of finding the particle drops to 0. This derivation proved that Bohr's early model was just one piece of a broader wave mechanical theory. The logic is consistent. We set up the potential, we enforce that the wave vanishes at the walls, and we find the discrete energy rungs that satisfy those boundaries. In the quantum world, the container is the primary author of the laws that govern the particle inside.
That was a Medhavy deep dive. Medhavy, AI-powered intelligent learning systems, on YouTube at Medhavy AI, medhavy.com. Subscribe for the next chapter.